Hello once again. It's time to warm up your brains and travel once again to the unknown lands of science. Although some of you might be a bit disappointed, I will continue to deal with the theoretical part of physics. In today's lesson, I want to discuss some quite exotic subjects, like relative motion, which is faster than constant velocity of light, or reversed flow of time. But I have to warn you, things might get quite complicated, so better prepare your brain cells for a serious workout. I've spent last couple months on researching Einstein's theory of special relativity and looking for an alternative solution to the problem of constant c in relative motion. Everything what you will hear in today's lesson will be based on things which I started to discuss in my last movie called Unified Relativity, Speed of Light in Relative Motion, and Objectivity of Observation. It might be pretty hard for you to follow my explanations without the understanding of mechanics in my model of relativity, unless you have proper education in physics or you are an actual genius. Generally speaking, this model is based on basic principles of Galilean relativity and doesn't use Lorentz transformation of coordinates. Velocities of moving objects are being added or subtracted depending on the direction of relative motion using the classic formula. All I did was to include the constant velocity c and maintain it in all frames. In this concept of relativity, order and simultaneity of events are definitive. I assume that there is only one timeline and it is valid for all observers. Observation of processes in own stationary frame is here treated as objective one, but it might differ from the observation of processes in relative frames. To put it simply, everything what we observe in our own stationary frames will happen in the same way for any other stationary observer. However, events which happen in frames which are moving relative to us might appear to be different from events observed in this frame from a stationary perspective. Processes might appear to happen in a different order in a moving frame, but there is only one objective timeline valid for all stationary frames. I will soon explain why it is important for my relativity model. In my model, rate of the time flow is not affected by the velocity of relative motion, so there won't be any kind of twin paradox if we exclude the gravity and acceleration from the scenario. Light moves at constant c in all directions from the point of emission, which appears always as stationary for all observers. However, a stationary observer is able to notice that a source of light is moving in relation to the photons which it emits, creating the Dopplers Effect. Due to Dopplers Effect, time might appear to flow faster or slower in a moving frame, but it remains in fact the same for all stationary observers. In the difference to Einstein's special relativity, time is here definitive and only space is relative. Light will move through different distances from the perspective of a stationary source and a moving receiver, but the distance observed by stationary receiver is treated as the objective one. Light, emitted 4 light years away, will need 4 years to pass that distance, no matter how fast the source is moving in relation to the observer. Only this way we can maintain the constant velocity of c in every frame. Speed of light is not affected by the velocity of its source. Let's now see how all of this works in practice. Last time I was discussing one of the simplest examples of relative motion. Two objects incoming at each other at 25% of c, and a third stationary object placed in the location where paths of motion intersect each other in one space dimension. Until today, there wasn't anyone who would accept my challenge and describe the scenario using special relativity starting from the perspective of one of moving objects. I don't think that it's possible to maintain the symmetry of relative motion due to relativistic velocity addition formula and Lorentz transformation of coordinates. Distance passed by objects will differ for stationary and moving frames. This is how this scenario is visualized in my simple simulation. Yellow sphere is here stationary, blue and red spheres are moving at 25% of c. In the bottom is the animation bar. Light moves through 1 unit of space in 10 frames. Red and blue spheres pass 1 unit of space in 40 frames, so they are moving at 25% of c. Paths of their motion intersect each other also in 40th frame. In classic Galilean model of relativity, from the perspective of red sphere, yellow sphere is incoming at 25% of c, while blue one at 50% of c and passes 2 units of space in 40 frames. Of course, because of symmetry in relative motion, blue sphere has to observe the same velocities and distances as red sphere. But according to special relativity, from perspective of red sphere, velocity of blue ball would be smaller than 50% of c, while for blue sphere, intersection of motion paths would happen in 45th frame. This of course would mean that the symmetry of motion would be completely gone and I would have to completely rebuild the simulation for each object. Special relativity appears to be incapable to handle the simplest scenario. Prove me wrong. This is how my scenario is represented on a time-space diagram. This is the perspective of stationary yellow sphere. Red axis represents space dimension, blue axis is for time, while yellow arrows are for the constant velocity c. Blue and red spheres pass the distance of two space units in 8 units of time, while their paths of motion intersect each other in 4th unit of time, 40th frame of animation. And this is the diagram for perspective of red sphere, after standard Galilean transformation of coordinates. Yellow sphere passes 2 space units in 8 time units, while blue one passes 4 space units in the same time. Paths of motion intersect each other still in 40th frame. And this is what we get in Einstein's special relativity. Simply absolute mess. Red sphere passes here much shorter distance in space than other spheres, while it should be the same as for the perspective of blue sphere. In shortcut, Einstein's special relativity is unable to handle this simple scenario in a way which could be used in a working simulation of relative motion in space. Relativistic velocity addition completely destroys the model. Instead of developing a completely new method of calculation for specific velocities of relative motion, physicists should make a model which works in all possible scenarios. There is absolutely no reason to assume that the Galilean model of relativity is not able to handle the constant velocity of light. I will now prove that you don't need Lorentz transformation to get valid results. Classical transformation of coordinates is just fine. On the animation which is visible on the screen, we can see the simulation of my scenario after the constant c was implemented to the Galilean model of relative motion. All I did was to turn all the spheres from my scenario into sources of light and make them emit a pulse of light each 10 frames of animation for the first 4 units of time. Right now, we're looking from the perspective of yellow sphere. Let me quickly explain the most important details. Small black spheres represent constant velocity c as it is observed from the perspective of stationary source. Small yellow balls mark the constant velocity c of light emitted by moving red and blue spheres as it is observed by the stationary yellow sphere. Yellow sphere at the bottom is here stationary, so it doesn't move in relation to the pulses of light which it emits. It's placed in the center of circles. Blue and red spheres are moving here at 25% of c, and their motion is relative to the light pulses which are emitted by them. Spheres are visibly displaced from the center of circular light pulses. Such displacement due to relative velocity of a light source creates a so-called Dopplers effect, which affects the frequency of observed light. But to properly describe the influence of Doppler's effect on time-space, we need to operate on the wave functions of light. Here is a comparison of light frequencies for a red sphere which moves at 25% of c in relation to a stationary yellow sphere. For the stationary yellow sphere, frequency of emitted light is equal to 1 cycle per 1 space unit in all directions. Here is the frequency of light which is emitted by red sphere in the direction of its motion. And this is the frequency of light emitted by red sphere in the direction opposite to its relative motion. Time at which light reaches a moving object might appear to be different for the perspective of its source and a stationary receiver. In such case, only the time at which emitted light was detected in receiving frame is treated as definitive one. In this particular scenario, light emitted by a stationary source seemed to reach an incoming object in 8th frame of animation. However, since in the moment of emission, receiver was placed 1 space unit from the source, pulse of light needs 10 frames to pass that distance, and this will be the definitive objective result recorded by a distant stationary light detector. To represent such model of relativity on a time-space diagram, we simply have to attach new axis of constant velocity c to the location of a moving light source. Below you can see the effect. Each impulse of light which is emitted by a moving red sphere has to be marked on the diagram by a new pair of velocity c axes attached to a specific location of pulse emission. Each time when axis of light is crossing the axis of time, pulse emitted by moving red sphere reaches stationary yellow sphere. I highly doubt that there is any other way of getting a result which is totally consistent with the animation. Of course, such model of relativity is valid only if we use the Galilean formula of velocity addition and classic transformation of coordinates. Here you can see a time-space diagram for the stationary perspective of red sphere. Just like before, pulses of light emitted by the blue sphere are reaching the red one each time when axis of constant c crosses the blue time axis. Let's see if, just like before, this time-space diagram is consistent with the animation. Small red spheres mark the constant velocity of light emitted by moving yellow and blue spheres as it is observed in the rest frame of red ball. As you might guess already, time-space diagram is matching the simulation in 100%. Of course, due to higher velocity of relative motion, Doppler's effect is much stronger for the blue sphere, which from this perspective seems to move at 50% of c. According to the simulation, due to Doppler's shift, time and space get 50% shorter in front of the incoming blue ball, while behind it, it is being extended by 150%. It's important that Doppler's effect is asymmetrical. Time-space gets 2 times shorter in the direction of relative motion, but in opposite direction it gets only 1.5 times longer. Try to keep this fact in mind, as I will come back to it in not so distant future, when I will try to deal with the problem of definitive time dilation, which is an experimentally proven process. Okay, if you manage to follow all those explanations, you are most likely ready to proceed deeper into the abyss of theoretical physics of time and space. But if you have absolutely no idea what the hell I was talking about all this time, or you don't know how I was able to maintain the constant value of c in Galilean model of relative motion, I strongly suggest you to watch my previous movie where I explain the details of things which I just presented. If this won't help, you can always ask for help in a comment, and if this won't help neither, then look for someone with authority in the field of relativity theory. I say this because from now on, things won't get any easier. I would say that it will get even worse. But before we will dive into unknown waters, I would like to speak just a bit about the contraction and expansion of time-space due to Doppler's effect and its influence on the perception of a frame in relative motion. Most of you heard probably about the blue and red shift of light emitted by distant stars which are moving in relation to planet Earth. My question is, however, if Doppler's shift causes effects other than change of length in light waves. In a couple of my last movies, I was mentioning the influence of Doppler's effect on the apparent rate of time flow in a moving frame. According to my claims, due to changes in wavelength of light, time can appear to flow faster or slower for a moving object. I think that some of you might ask if I can support such radical claims with any kind of experimental evidence. And since this subject will be crucial for things which I'm about to discuss, I need to dispel any possible doubts as for measurable distortions in perception of time flow due to Doppler's effect on frequency rate. To be honest, this will be much easier than some of you might expect. You have only to keep in mind that Doppler's shift is not limited to the wavelength of light, but works for all kinds of waves and their frequencies. Almost all of you experience the effects of Doppler's shift on acoustic waves. All you need to do is to stay for a while next to a busy highway, or listen to a siren of a speeding ambulance. This is what I mean. But of course, the changing pitch of a sound due to Doppler shift is a well-known and documented process, and it doesn't prove my claims regarding the actual change of time flow rate. And this is why I won't speak here about the tones of a sound. What I have to do is to look for a sound of a random mechanical process which takes place in a determinate cycles. I could use ticks of a giant analog clock or a monotonous beat of a drum. There are countless examples of such processes. But because the source of such sound has to be in motion, I decided to use the sound of an engine. I spent some time looking for the best example, and I ended up with the sound of a helicopter, which is passing at low altitude. I couldn't find What I need to do right now is to count the number of chops in a defined period of time. for the sound of incoming chopper and are recorded when it is flying away from the observer. Luckily, I know how to do it using a known music production software called Fruity Loops. This is the entire audio track from the video which you saw. I slowed down the entire sound wave and added some filters to reduce the noise and increase the volume of engine chops. Those are the parts which I'm interested at most. I will now count the number of chops in free time units for the sound of incoming helicopter. I counted 20 chops in 3 units at time. And now let's focus on the sound of a chopper which is moving away from the observer. And now let's count how many chops fits here in 3 units of time. And it seems that when chopper is moving away, there are only 15 chops in 3 units of time, 5 less than for the sound of incoming helicopter. And this proves clearly that besides the noticeable distortion of sound and visible light, Doppler's effect has a measurable influence on the apparent rate of ongoing processes. But does it mean that time is flowing at a different rate for the moving chopper than for someone who is standing on the ground? The answer is simple. No. Time is in fact flowing at the same rate in both frames. Distortions caused by the Doppler's effect are completely relative and doesn't affect processes observed in a stationary frame. Clock on board the flying helicopter will count the same amount of time as a stationary clock which is placed on the ground. But now you might ask, why in such case Doppler's effect is so important for my model of relativity? And this is the right moment to discuss another scenario. Although just like before we have here 3 objects which are moving through space towards each other, there are 2 crucial differences between those 2 scenarios. First of all, in this case, from the perspective of a stationary yellow ball, red and green spheres don't move anymore with the same velocity. In this scenario, red sphere is moving at 50% of c and passes 4 units of space in 80 frames, while green one moves at 75% of c and in the same time it moves through 6 units of space. And it's those particular velocities of relative motion which make the most important difference. Some of you know probably what I mean. If you don't understand the issue, I will use a time-space diagram to explain what is the general problem of this scenario. This diagram represents the perspective of stationary yellow sphere and motion of other objects in relation to light which they are emitting. For now everything seems to be working just fine. But the problem becomes clear if we change the perspective to one of moving spheres. This is the diagram for the stationary perspective of red sphere, After using the classical formula of velocity addition and transformation of coordinates, it becomes clear that now relative velocity of green sphere seems to exceed the speed of light. For the rest frame of red sphere, yellow ball is moving at 50% of c, while green one moves at 125% of c, and passes 10 units of space in 8 units of time. According to special relativity, this situation can't happen, as nothing can move faster than light. To avoid such possibility, Einstein created a new formula for velocity addition in relative motion and forced the use of Lorentz transformation when we change the point of view to a different frame of reference. Those are the formulas for velocity addition in special relativity. As you can see, they include much more parameters than the classical one. I could try calculating the relative velocity of green sphere from my scenario using those formulas, but I'm a lazy person, so I decided to use an online calculator and got a velocity equal to 0.909 c. So it seems that special relativity is able to maintain one of its main postulates and prevent the relative motion at velocities faster than constant c. Problem is that now the result is completely inconsistent with the distance which is being passed by green sphere. If I would try to use this result in the simulation, I would have to adjust the distance to relative velocity of green ball and completely rebuild the entire scenario to change the perspective. And then, if I would try to switch the perspective back to yellow sphere, I would end up with results different than values on which I base the whole scenario. In shortcut, it's completely impossible to use the special relativity in a working simulation of relative motion. And once again, I will now ask all the viewers with proper education in this field, prove me that I'm wrong, by creating a working simulation of any scenario which I presented in my movies using the mechanics of Einstein's special relativity. I would really love to see how it works and gives some valid results. But since up until now there wasn't anyone who would try to accept my challenge, I will simply continue to use a model of relativity which is able to work in practice. But this means that now I need to decide what to do with a relative velocity which is higher than c, and as always I will choose the simplest possible option. In this case I just won't do nothing and see what will happen. And this is the result. Are we still alive? Did the universe collapse or disintegrate? Does the fabric of time-space still exist? Honestly, I didn't notice any of those issues. Reality still seems to be functioning properly. Amazingly, my simulation didn't cause any critical errors in the universal code of nature. Hooray! It seems that I've just broke the holy law of Einstein's relativity and nothing actually happened. For the stationary red sphere, green ball seems to move faster than the light, which it emits. It seems as well that my computer didn't explode and was able to compute the simulation properly, despite the critical override of laws in Einstein's relativity model. In such case, let's see what kind of impossibility did we get in the predicted results. This small and unmanly pink sphere represents the constant velocity c as it is observed in stationary frame of red sphere. Let's start from the fact that in the first frame of animation, distance between red and green spheres is equal to 10 space units. Impulse of light emitted in the first frame needs 10 units of time to reach the incoming sphere. However, since green sphere is moving at 125% of light speed, it passes this distance in 8 time units, 80 frames. If you belong to the smarter part of audience, you should be able to notice that something interesting takes place in the animation. Of course, not everyone is a theoretical physicist, so allow me to explain the issue with this image. As you can see here, all pulses emitted after the initial event are reaching the red sphere before the first pulse gets there. It's even better. Pulse emitted as last one in order, in 40th frame, gets to the incoming object as first one, turning the proper order of entire timeline upside down. In shortcut, according to the simulation, everything what happens in a rest frame will appear to happen in reverse in any frame which is incoming at relative velocity of 125% c. As for a scenario which is supposed to be completely impossible, such result appears to be quite logical. Even if special relativity order of events can be sometimes reversed, due to Lorentz transformation of coordinates. But better let's see if all of this is consistent with my time-space diagram. To To do it properly, for each emitted light pulse, we need to place the axis of constant light speed in the proper point of space and the right moment of tie length. To keep the clarity of diagram, I included only 3 pulses, first and last one, and one more in between. According to diagram, pulse emitted in 40th frame of animation, 4th unit of time, reaches red sphere in 9th time unit, while light emitted in the first frame arrives 1 time unit later, in 100th frame. Other pulses are distributed in reverse between those two. It seems that as for now, everything is working nicely, and the impossible scenario has in fact a logically valid and physically possible solution. Of course, I am fully aware that most of professional scientists will deeply hate my simple solution to higher than c relative velocity. Einstein told clearly that nothing can move faster than light. My explanation is just an abomination of the sacred theory of relativity. Impossible situations can't have a simple solution. How dare I to undermine the assumption of impossibility? Who am I to disagree with the greatest mind in the history of theoretical science? It's a pure blasphemy to propose such plain and obvious solution to some of the greatest problems in the theory of time and space. Physicists spend their whole lives to get a grasp on this divine knowledge, and yet I dare to believe that it's possible to explain the basic model of physical reality using a 3D software. How can I think that any properly educated scientist will treat seriously a model which doesn't need any mile-long chains of sophisticated calculations and doesn't require decades spent on academic education? Professional scientists won't waste their time on pseudoscientific theories which are not supported by any serious calculations and can be proven experimentally. And since nothing can move faster than light, my claims don't have any scientific base. Oh yes, about that. Well, I'm really sorry that I have to disturb your outlook on Einstein's theory of relativity, but it seems that like in many other cases, my pseudoscientific claims regarding faster than light motion, FTL, and reverse time flow should be in fact considered as yet another experimentally proved law of physics. Well, you have to try living with it. According to an article from iflscience.com, which is called "Going Faster Than Light Could Send You Back in Time," everything what I said about this subject is fully consistent with the results obtained from practical experiments. Just listen to this. An international team of scientists set up experiments to simulate what a stationary observer would see when looking at a superluminal faster-than-light event. In their paper, published in Science Advances, they demonstrated that if a light source approaches the observer faster than the speed of light, then the images appear to move backwards in time. And what now? Here's the original publication called "Observation of Image Pair Creation and Annihilation from Superluminal Scattering Sources" in PDF format, link below. It seems that the reverse order of events was observed both in the light and in the sound waves, when their sources broke the barrier velocities. Of course, all the articles are stating clearly that no one didn't in fact break the limit of velocity c in their experiments, and that superluminal speed was reached by shining a laser beam at different points on a projection screen, making the laser dot to appear as moving faster than photons, which make the beam itself. But does it disprove my claims? Not at all. You see, even if the source of light appears to move faster than constant c for one of the objects in my scenario, for another object the same source is moving slower than the light which it emits. Of course, from the perspective of this source, emitted light is moving always at constant c in all directions of space. Superluminal speed is the result of velocity addition in relative motion, and is not caused by actual acceleration of a light source. All the apparent paradoxes and misunderstanding in the theory of relativity come from a single yet crucial issue. For some unknown reason, physicists seem to completely overlook the difference between constant speed of light and velocity of relative motion. Both values are described by distance in space passed in a period of time, but they have to be treated in a completely different ways. Moving with the speed of light doesn't mean to become a photon. Since until now no one still didn't define the difference between speed of light and a relative speed of objects, allow me to briefly describe the basics. There are two types of velocity: constant c and velocity of motion in relation to constant c. Velocity c is constant, the same in all frames of reference, and is independent from the velocity of relative motion. Relative velocity is variable and depends on relative velocities of reference objects' frames. In relative motion, velocity and distance is apparent, and depends on the direction in which objects are moving in relation to each other. Operating on the relative velocities requires a transformation of time-space coordinates. Velocity of light in a vacuum has a constant value, and the only operation which is allowed, or rather forced, is to maintain its constant value for all frames in relative motion. Light propagates only in the direction of its emission, and doesn't have a rest frame. In a vacuum, photon can't change its velocity or direction of motion. Once a photon is emitted in the direction of a receiver which moves in relation to the light source, it will always get to the destination in the time which is defined by constant velocity c. Change of direction and speed in relative motion won't affect the final result, which is determined in the moment of light emission. Motion of objects in relation to emitted light can be observed only in the rest frame of light's receiver. Distance passed by light might appear to be different from perspective of the source and the receiver. I think that those are the most important differences between c and other velocities. I can bet that some of you will tell now, hey, you forgot about a very important aspect of light speed in relative motion, the one which tells that nothing can move faster than c. No, I didn't forget about it. Relative velocity of a light source can exceed the speed of emitted light due to relative velocity addition. Until in the rest frame of a light source constant c is being maintained, I don't see any issues with such possibility. However, there is a clear limit of relative velocity. Constant c can be reached or exceeded by acceleration of a single object frame. As in the rest frame of a light source, light has to move at 100% c in all directions. The only way to break the constant speed of light is to accelerate a second object frame in opposite direction to the relative motion of a light source. This means that it's physically impossible to create a scenario where in a stationary frame we will be able to observe two objects moving at FTL velocities in opposite directions in relation to each other, or at least I don't know how this could be done. This is why I am able to guess that a relative velocity equal and higher than 200% of c is in any case impossible. But of course I might be wrong. Okay, I think that since I clarified the most important aspects of constant c in relative motion, we can go back to my scenario. However, there is one more thing which still has to be done. This scenario in its current form has a big issue. Timeline of the relative motion ends after 80 frames of animation. After this period of time, objects stop moving in a point of space where their motion paths intersect each other in a single space dimension. However, the scenario doesn't end after 8 units of time, as light emitted by green sphere in first frame of animation needs 2 time units more to reach the red ball. During this time, spheres are not moving anymore. This means that I would have to consider the acceleration and deceleration of moving objects as a factor which might affect the apparent time flow in relative motion. This subject needs, however, a much deeper and more detailed explanation, and we are not there yet. I'll try to discuss it in next movie. For now, I will simply modify slightly the scenario and make all the objects to cross a single point of space dimension in the middle of timeline. That means exactly in 40th frame of animation. And this is the result. Now it is much more similar to the scenario from my previous movie. I hope that you know already how to read time-space diagrams. This one describes the stationary frame of yellow sphere. And this is the diagram for stationary frame of red sphere. And here is a third diagram for the stationary frame of green sphere. The only thing which differs the perspective of red and green spheres is the relative velocity of yellow ball and the directions of motion. This is why I won't waste the time to apply those values to the simulation. This is how looks the animation after the modification of scenario. But let's now focus on the most interesting part, which is the relative FTL motion of red and green spheres. For now, I got rid of the yellow sphere and spent some time on creating the modified grids of space coordinates. Of course, due to the symmetry of relative motion, relative velocity of the incoming object will be the same in rest frames of red and green spheres. In shortcut, after changing the perspective to the green sphere, I will end up with the same result. Let's now go into the details. I'll begin with the most important aspect of time flow in relative motion, that is, the proper order of events in timeline. This violet spiral represents a clock which counts the passing time. Since both spheres meet each other after 4 units of time, in this time clock has to count 4 cycles. Problem is that in this case we have to take into account the fact that due to relative faster than light velocity of motion, for the stationary red sphere, time clock of green sphere will appear to run backwards. Question is, if it has any meaning for the time flow observed by green ball in its rest frame. According to Einstein's special relativity, time flow is relative, and events can be observed in different order in rest frames of objects in relative motion. This is why, according to many scientists, time can in fact flow backwards for green sphere. But in my model of relativity, order of events in timeline is definitive and has to be the same for all stationary observers. Reverse time flow is only a result of inverse Dopplers effect in the relative FTL motion. It means that for both objects, time has to flow in the same order and at the same rate. In special relativity, time would flow for both objects at different rate or even in different order. For example, green sphere should experience less time than red one because for stationary yellow ball it is moving faster and passes longer distance than red sphere. But of course this can't be true, since without any reference to yellow sphere, both objects are moving with the same speed in relation to each other and move through the same distance. This means that time has to flow at the same rate in both frames. But now let's see how I modified the space coordinate grids. Red part is stationary for red sphere, green part is stationary for green sphere. And now let's see how to transform space coordinates to maintain the constant c in both frames. Let's compare the distances passed by light in first 10 frames of animation. White lines mark the distance of 1 SU, space unit. Yellow lines mark the distance which is equal to 0.25 SU. Black marbles represent light as it is observed in rest frame of green sphere. Red marbles represent light as it is observed in rest frame of red sphere. Yellow marbles represent light as it is observed by yellow sphere. White waveforms show frequency characteristic to rest frames of all spheres, 1 cycle per 1 time unit, TU. Black marbles travel at velocity c. During 10 frames of animation they pass 1 SU. Red marbles pass the distance of 0.25 SU and 2.25 SU. Yellow marbles pass the distance of 0.25 SU and 0.75 SU. And now let's speak about the weirdness of this situation. Let's begin from the fact that light emitted by green sphere in the direction which is opposite to its relative motion appears to move backwards for stationary red sphere at velocity equal to 0.25 c. This is why I've decided to modify the wavelength of light characteristic for rest frame of green sphere to match it with coordinates of red sphere. Wavelength is now 4 times shorter and still maintains the constant velocity c in rest frame of green sphere. To maintain the balance, I will try to modify as well the waveform on left side of the green sphere. Let's compare the distance passed by light in rest frame of green sphere to space coordinates characteristic for red one. It seems that 1 space unit in rest frame of green sphere equals to 2.25 space units on coordinate grid of red sphere. I will be honest, this is the value which I've got from the simulation, and at this moment I have no idea why the ratio equals to 1 to 2.25. I'll let you know after I figured it out. But just like before, I changed the wavelength of waveform, which is characteristic for light in the rest frame of green sphere, to match it with coordinates of red sphere. And once again, despite much longer wavelength, modified waveform still maintains constant velocity c in the rest frame of green sphere. For now, we were looking at the scenario from perspective of stationary red sphere, but now is the time to change point of view to the rest frame of green sphere and see what happens with the distance which is being passed by light in 10 frames of animation, or 1 time unit. What matters here is the distance passed by light which is observed in rest frame of red sphere, which is marked here by red marbles. Let's begin from the one on the left side. It seems that 1 space unit characteristic to rest frame of green sphere is equal to quarter space unit of red sphere, only in reverse. And this is the waveform which matches such direction and velocity. And now let's deal with the red marble to the right. It seems that once again the distance is equal to 2.25 SU, and this is how looks the waveform characteristic for such distance. To summarize all of this, let's now look at the entire scenario with all three spheres visible. And this is what matters at most. Despite all the modifications of coordinates and relative faster than light velocity, in 40th frame of animation, distance and time count is maintained in all frames exactly as my model requires. But the final question is, what actually happens when red and green spheres meet each other in the middle of timeline? Well, it might sound strange, but obviously the incoming object arrives before it can be seen in the rest frame, and while it is moving away, timeline of events which already took place in the moving frame is being observed in reverse. Until both objects continue their relative FTL motion, there is absolutely no problem with the apparent reverse of time flow. Strange things would start to happen if the relative velocity would drop below c, but this is a subject for another lesson. I think that this is more than enough for this movie. In the next lesson, I will discuss the greatest mistake of Einstein's relativity. That means the problem of his famous light clocks and the solution which he proposes in special relativity. Class dismissed.